Hey everyone, this is Dr. Walker. In this video from 526, we're going to do another example of finding the electric potential due to a continuous charge distribution. This example is going to be a line of charge, and we're trying to find the electric potential at point P, which is above one of the endpoints of the rod. We didn't do the exact problem for electric field, we did a similar one where we found the electric field above the midpoint of the rod, but we'll be using the skills that we learned in that example in this example. So the first step is always to divide up our charge distribution into a bunch of little elements, dq's. And in this case, dq is just going to be along the x-axis, so we know that we're going to integrate along the x-axis. We're going to write the potential due to that one little charge element, dv, as ke integral of dq over r. And then we can make our usual substitution that dq is lambda dx. And for r, we know that using the Pythagorean theorem, that it's equal to the square root of a squared plus x squared. We can go ahead and write that down, a squared plus x squared. And we know that as we're looking at the potential due to every single point, we know that the r is only changing because the x is changing. So by writing it in terms of a and x, we can now integrate along the x direction to get the contribution of all of the dq's. So that means we're going to integrate from 0 to L, the length of the rod. Now this integral is a little bit tricky, so you can use your calculator or integral table. And when you get the answer to this integral, I don't expect you to be able to solve it. It's going to be the log of x plus square root of a squared plus x squared. That's the integral, and then we're going to integrate we're going to take the limits from 0 to L. So now we can go ahead and plug those in. And sorry, this was supposed to be V, not dV. Sorry about that. All right. So now our potential at point P here is going to be ke lambda. Then we're going to put in the limits. Log of L plus square root of a squared plus L squared. And then we're going to have minus log, and then we're going to put the 0 for x, but then we're going to still have a squared when we put the 0 here. Square root of a squared is going to be a. So we're just going to have log of a when we put in the 0 here. And we know that we can simplify two logs by writing them as a ratio whenever you have a difference of the logs. So our final answer is going to be ke lambda log of L plus square root of a squared plus L squared divided by a. So that is our potential at point P. If we wanted, we could write lambda here as charge per length, since we are given in the problem that there is a total charge Q and there's a length L. But we can also leave it in terms of lambda since we are also given the lambda in the problem. So you just always want to write the answer in terms of variables that we are given in the problem. That's it for this video. I hope that you understand how to find the potential due to continuous charge distributions.